In this video we're going to talk about the floating point representation of a number, and let's say the number is x. And what do we mean by the floating point representation? Well, every number is stored in the computer as a sequence of bits, and this is the bit map for a floating point number. It has three parts, or that bit map is broken into three parts. One bit is dedicated to the sign of the number. 8 bits are dedicated to the exponent of the number, and 23 bits are dedicated to the mantissa of the number. Now, what does all that mean? Well, let's have an overview of what's going on here. In general, a number can be expressed as some sign plus or minus 1 point, let's say 75 to start with, times 2 raised to some number, let's say the third, just to pick a number. The sign bit determines the plus or minus. The mantissa bits determine the 1.75, and the exponent bits determine the 3. And we'll get into the details of how that occurs in a second, but right now just realize that always you should think in this form. There's a plus or minus in front of the number, and we'll just assume it's plus for a second. It'll be easy to see how that's handled. The important thing here is to note that this mantissa, the mantissa part, is always some number between 1 and 2, and not including 2. It could be something like 1.9999999, sort of. You'll see what I mean by sort of in a minute. The idea, it can get very close to 2, but it will never be 2. And it can be 1. The mantissa can be 1. In other words, it could be 1.0 if you like. So that's the mantissa, and we'll see how the bits up here are converted into that mantissa part in a second. Now, there's also the exponent part. It's always going to be base 2 raised to some exponent. So let's see how all that comes together now. How does this thing, this bit map, get translated into this number down here? And let me start. I don't want to start with this number. We're going to save that for an example for later. Let's just start with 1. Here's how it works. Leaving aside the sign bit for a second, the first element is the sign bit. The second grouping are the exponent bits, and there are 8 of them. And what the computer does somehow is it extracts those 8 bits and then turns them into an integer. And it does it in the usual way. This is the binary representation of some integer. So it corresponds to, in this case, 127 is the decimal equivalent of this binary number, and we'll look at that in a little more detail later. What it does with that exp then is it subtracts 127 from it, and in this case this binary number translates into 127, and so then x minus 127 is 0. So in that case, 2 to the x minus 127 is 1. In other words, this little piece down here, this multiplier, is just 1. Now that's because I picked a very specific number up here. Let's change that. Let's suppose I chose as my number up here, let's pick some multiple, some power of 2. Let's pick 2 raised to the 8th. Now, look at what happens here. 2 raised to the 8th. Notice it comes out here as an 8. And intermediate value is 135. In other words, the exp collection of bits up here in the bitmap translates into 135, but we always reduce that by 127 to end up with the actual exponent. So in that case, this comes out to be 256, just as we would expect it to. So that's how the the exponent part of the calculation works. Notice it's a three-step process. You first extract the 8 bits, you convert them to an integer, you subtract 127 from that integer, and why 127? Well, we'll see in a second. And then you raise 2 to that power, and that's what you multiply the mantissa by to get your final number. Now let's talk about the mantissa. Here's the formula for it. Let's look at the formula. It's written out here, but let me make it a little bigger so we can look at it in some detail. Here's the mantissa. It's 1 plus the mantissa. There are really 3 phases to the mantissa. So what's really the mantissa? Is it the first phase or the last phase? Well, I'm going to use it interchangeably for all phases. It'll be clear from the context which phase I'm talking about. So originally the mantissa is just the final 23 bits of the bitmap. So the computer extracts them first, and now it's just a bitmap with 23 bits in it. And what it does with that, it divides it by 2 to the 23rd and gets some fraction. And let's put a number in here that will give us a little more. Let's suppose we put 2 to the, let's say 1,000. Okay, so this is how the computer stores 1,000 in its bit schema. This is the mantissa part. So if we extract that, we get this. If we convert that into a number, this is binary code. This is the decimal equivalent of that binary code. We get 7,995,392. And then we divide that by 2 to the 23rd. Now why by 2 to the 23rd? Well, we'll come back to that. It'll be pretty clear. And then finally we add 1 to it. And this then is the mantissa. And so this part in here is always going to be a number between 1 and 2. 1 and 2. And let's see why that is, and why that we use 2 to the 23rd as our divisor. So let me reverse my order of inputs here. Now I can put in whatever input I want here. Let's suppose I put in suppose my mantissa ends up as just 1. Notice what that means in terms of the bitmap. There's just a 1 here at the end. And if I divide it by the 2 to the 23rd, I get this thing here. And incidentally, this is called the machine precision of the computer. If you're dealing with a 32-bit computer, that would be called the machine precision. And that's, in some sense, as close as you can get to the actual value of a number. Your error could be as great as half that. All right, but let's let that go for a second. So the question is, what's the biggest number I could put into the mantissa part here? How would this be at its largest? Well, it would be as largest if they're all 1s. And that's where the 2 to the 23rd comes from. If I put 2 to the 23rd in here, I get all zeros, because 2 to the 23rd, this is the 0 slot, and the 23rd slot would be over here. It doesn't exist in a 32-bit number. So this number is too big for a floating point number. So what you have to do is subtract 1 from it. And now notice they're all 1. So that's the largest number you can put in the mantissa, is this 8,388,607. And now if you divide it by 2 to the 23rd, that's always going to be bigger than the mantissa. That's why this number here is always less than 1, and therefore this number down here is always going to be less than 2. In fact, this is as close as it can get. It'll never get any closer than this. We can make it exactly 1, and that's easy enough. Let's just put a 1 in here. And you know, there is the mantissa is actually equal to the machine precision then when this is a 1. All right, let's talk about error and machine numbers. What's a machine number? Well, first of all, let me make my exponent 0 here. So my multiplier down here is just going to be 1. And we'll start with that. To do that, I have to make this 127. And now my exponent minus 127 is 0, so my multiplier is just 1. Now, let's go over here and do what? What do we want to do here? Okay, we want to talk about machine precision, and let's do that with an example. Let's suppose I put in here, I want to reverse the way my program is working here, so let me click on this. I want to go the other way. Suppose I put in here as my x 1 plus 1/3. And let's see how close a floating point number can get to 1 plus 1/3. To do that, let's bring up our calculator. Now I've set this up ahead of time. Here's our formula for the decimal equivalent of this bitmap. So the floating point equivalent for this x, and the x is 1.33333. It keeps going. That's what 1/3 is. Infinite number of 3's going out here to the right. Notice what our floating point number comes out to be. It comes out to be 0.33. Let me reduce that. Let me reduce that. Less decimals. We can get the point across with just a couple of decimals out there. All right, so this is our approximation, our floating point approximation right here in the middle. And notice it is an approximation. It's off by 4. If we just look at the last 2 digits here, we're at 37. We should be at 33. That would be a better approximation of x. So we're off a little bit. But that's really the best we can do. If we take our mantissa and increase it by 1, in other words, that would give us the next machine number, the next higher machine number. If we increase the mantissa by 1, we get 49, and now we're off by what, 16. 33 to 49 is 16. So certainly this is a better approximation than that. Suppose we reduced our mantissa by 1. In other words, we looked at this thing here. In that case, our machine number, each of these are machine numbers. A machine number is something that can be represented by an integer value for the mantissa. And in that case, we end up with our last 2 digits being 25, which is off by what? It's off by 8. If we compare this to what we'd like it to be, our machine number is off by 8 units in the last 2 digits. So clearly this is the best machine number for approximating this value here. Now look at the gap between these machine numbers. Remember, these are successive machine numbers over here, and that's because the mantissa in each case is incremented by 1 as I move from here to here to here. The gap between them is 25 to 37, which is 12 units, however far out we are. And then again, from 37 to 49, it's 12 units. And that is precisely machine precision. That is precisely epsilon. So epsilon tells you the gap between machine numbers, and therefore the error in any given number can be up to 1/2 of that. In the case of 1 1/3, we see that the error is 4/12. So that's in keeping with a bound of 6/12. It could be up to 6/12 if our real number fell exactly in the middle of two machine numbers. Now watch what happens if we multiply our x by 2, say. Remember, the mantissa is always a number between 1 and 2, not including 2. So if I multiply this by 2, I'm always going to end up with a number between 2 and 4, not including 4. Look at what happens to the error now, or let's call it the gap between machine numbers. These are the machine numbers for anything between 2 and 4. And if you look at this difference now, it is 24 units. If you just look at the last two digits, it's 24. And then 24 again to get you up to 98. That's twice machine precision. So, that's 2 times epsilon. So every time you multiply this by 2, you get another range of numbers. If I were to multiply this by, let's say, 8, then I'm going to get a range of numbers between 8 and 16, not including 16. And now my error between numbers is going to be 8 times epsilon, or my gap between machine numbers is 8 times epsilon. So my error could be up to 4 times epsilon, because I'm always going to round to the nearest machine number. So I'm not going to be off by more than half of some multiple of epsilon. Let's see if that's right. If I take this one here, that's the lowest, that's the lower machine number. And if I add, let's just do it this way, plus, okay, I want to do plus 8 times the machine error. And let's put that back in here so we get the same number of decimal points. And there I get it. I get the next machine number up there. So every time I multiply my x by some power of 2, I widen the gap between machine numbers. Now it goes the opposite way too. If I were to multiply this by 1/2, my exponent then is going to be -1, so I'm going to be multiplying everything by 1/2. So with that kind of an exponent, I can represent numbers between 1/2 and 1, not including 1. And my error now gets cut by 1/2 because the gap between machine numbers is now 1/2 of epsilon. So let's just see if that's the case. We can change this here, and we make this 8 1/2. Okay, this number should match our middle number because I'm taking my lower number and adding half of epsilon to it, and it does match. So machine epsilon, the error, or the approximation error, depends on this exponent over here. The bigger the exponent is, the more your potential error is going to be. It doesn't have to be that big. I mean, you could put in a machine number up here and then you'd have no error. But you could put in a number that's exactly halfway between two machine numbers. Let's put in something that's halfway between two machine numbers. And that's easy enough to do. We'll just take the average of two machine numbers. So we'll say 1.5 is one machine number plus epsilon over 2, and that will give us a real number halfway between two machine numbers. Now 1.5, any power of well, like 1.5, that's 1 plus 1/2. So that is a machine number. 1 plus 1/2 is a machine number. Then I add half of epsilon to it. I end up with a number halfway between two machine numbers. So what does it do in that case? Alright, so it should be a 1.50006 way out here. And what is it? It's a 0. So I'm off by 6 units. I'm off by exactly half of machine epsilon. So that all makes sense. Now, what else do we want to talk about? One other thing. This function up here, float, this takes a double, machine double, which is, most machines are at least double precision instead of 32-bit or floating point precision. But I can take a 32-bit or 64-bit number and convert it into its floating point equivalent with this function. So I do that just to show that our calculation here is doing exactly what the machine is doing. So let's go back to 1 plus 1/3. The machine says that as a floating point number is this with the 37 on the end. Our calculation shows that it's the same thing. So that's sort of confirmation that our formula, this formula down here, is exactly what the machine is doing when it converts numbers into floating point numbers. Now, let's say one thing about the sign. The sign is pretty easy. If this is 1, if we look down here, then this thing here is minus 1 to the 0, which is just 1, so that gives you a positive number. Now if I make it, let's make this a minus here, put a minus in front of the whole thing. Now the sign bit goes to 0, so down here in the formula it now becomes minus 1 to the 1, which is minus 1. So that's how the sign bit figures into things. Now what else can we say? Let's just play for a second, just to see that we understand what's going on here. And let me go in the opposite direction. Suppose, let's forget about the exponent. It's pretty simple. Oh, okay, actually there's one thing we want to say about the exponent. Why the 127? Why the 127? Well, we want to allow for fractions here. Remember, the mantissa part is always a positive number between 1 and 2. So if we want to end up with fractions, then this 2 part, we have to allow for things like 1/2, 1/4, 1/8, and so on. And the way we do that is we subtract x, we subtract from x 127. Remember, x as it's held in the computer has to be a positive integer. In this case it's 127. So if we didn't do anything to that x, we would always end up with some multiple of 2 here. Maybe it's 2 to the 0 or 2 to the 1 or whatever. So we've got to reduce it in order to allow for multiplication by fractions, by things like 1/2, 1/4, 1/8, etc. So the smallest fraction we can make here, or why 127? Well, we could make this anything we want. We could subtract, subtract. Well, the biggest this number can be is 255. We could subtract 254. If we did that, though, our only positive multiple then would be 2. So that would very much limit us on the upside. Or we could make it our subtraction 0. If we do that, then we would have no fractional multipliers here. So the idea is to choose a number that gives you a nice divide between the fractional multipliers and the positive multipliers. And since the maximum number that we can achieve here is 255, seems like a good middle point. There is no middle point exactly as an integer. The middle point is what? 127.5. So a good choice for this thing we're subtracting would be either 127 or 128. Let's choose 127. So that's where the 127 comes from. And again, what about the 2 to the 23rd? I've already mentioned this, but that's the biggest number that can be, well, that's actually 1 greater than the biggest number that can be represented by this string of bits here. Let's put the biggest one in there. The biggest one you can get in there is 8,388,607. And that is 2 to the 23rd minus 1. So this number here, once we divide by 2 to the 23rd, is always going to be less than 1. So our mantissa part is always going to be less than 2. Now, one final thing. Here's a problem to think about, and took me a while to fully understand it. So let me give it to you. Suppose we're given an x here, and I want to know, is there a formula for converting it, or for extracting from that x this number here, the x part, and this number here, the mantissa part. So suppose I plug in an ordinary arbitrary number. Let's say that there. Is there a way to manipulate this x so that I can pull out this exp and this mantissa? And there is. You just take the formula. This is the formula for x down here. So let's well, before we do that, I want to point out one thing. Let's clear this. I think we're through with all this. If I have a number of this form, 1.9999 times 2 to the 5th, say, how would suppose I didn't know that it was exactly this form. I just knew that it was, this. I just knew x. Actually, let's put that in there. Let's suppose x is that number there. 1.9999 times 2 raised to the 5th. So I don't know that there's a 5 here, and I don't know that there's a 1.9999 here. Actually, I want to change that. Let me make it a machine number. Let's suppose it's 1.75, just to keep it real. Let's suppose we have this number here, and we want to know, how do I compute this exp and this mantissa directly from that number? I don't know them, I just know x. Well, you use this formula here. We have this formula. Let me see if I can get it up here. Okay, but before I do that, I want to point out one thing. I want to look at a simple example. Suppose I have this number here, and how can I pull out the 175 and pull out the 5 not knowing them directly? All I know is it's 56. Well, here's how I would do it. I would first focus on the 5. We're going to try to pull the 5 out of there. And the way you would do that is you would take this number you would take the log to the base 2, say. You could take just a regular log, but the math is a little more direct if you take the log to the base 2. Okay, so I'm going to, let's say x is equal to that. And again, I don't know this side, I just know x. So how can I pull the 5 out of just my knowledge of x? So first thing I do is I log both sides. Undo. Why didn't that work? Oop, because I shouldn't have a question mark there. I should have a $sign. Okay, so I'm going to log both sides. And then I'm going to use a property to log. The log of a product is the sum of the logs. So let's see if that's one of our stored properties for log. That should be. There it is. So that breaks that up. And now notice what this thing is here. The log to the base 2 of 32, it converted my 2 to the 5th to 32. This thing here is just that 5 that I'm looking for. You know, this thing here is just 5. And that's what I'm searching for. Again, I don't know it. I just know this side. I know what the log of 2x is. I know it's the n I'm looking for plus something else. But let's look at that whole thing, what that thing is. Notice it's 5.8073. It's got the 5 in it that I'm looking for plus some number which is less than 1. And this has got to be less than 1 because the mantissa, remember the mantissa is always less than 2, so the log to the base 2 is always less than 1. So this part here is always going to be less than the next integer. So if I round both sides, suppose I round both sides of this equation, I get this thing here, but rounding this thing is just 5. In other words, this side of the equation is just 5. It's the 5 I was looking for. So, you know, I didn't have to know the mantissa to solve for round. Doesn't like round. Oh, because you got to tell it what you want to round it to. 1. You should be able to. Well, that didn't work out at all, did it? Why did that not work? Alright, well, that didn't work because I wanted to go down. I was 5 plus something. I don't want to round. That would round me up to 6, so that's not going to give me what I want. I want a floor. So this should be floor over here. That's that's my mistake. So I take the floor of this thing, and I don't need the 1 in there when I'm dealing with floor. And now we got it. In other words, to get the exp, I take the x that I started with, I take its log to base 2, and then I take the floor, and that'll give me exp. So let me look at that one more time. You know, we take this formula, and we know that x is equal to that, and the sign's easy enough. You know, this part is easy enough to compute. That's no problem. So it's really this part that's the tricky part. And in general, you look at this and say, well, this is an equation with 2 unknowns, so how can I solve it? It should be a variety of solutions. You know, I pick an x, any x I want, then I solve for the mantissa. Well, it doesn't work that way because the particular properties of this mantissa section, it's always less than 2, and so when I take the log to the base 2, it's always less than 1. So I know that this number here is going to contribute a fraction to my calculations. And I can get rid of that fraction no matter what the mantissa is by taking a floor of my ultimate formula. So again, the formula is this here. To get the x, I take the floor of the log the base 2 of x. And that gets you the 5. Let's look at that. I'm going to just plug in some more numbers here. Whatever I put in here, let's say 3,487. Notice my x is 11 and my formula gives me 11. So that way I can calculate x directly from the number x up here. Now what about the mantissa? Well, that you can just solve for. You have this fact. You have the fact that x is equal to this thing here. And again, the sign is no problem. We can always get the sign from whether it's greater than 0 or less than 0. So the problem is this: how do we get the mantissa out of this thing? Well, we know the x at this point, so it's an equation 1 unknown, so we just solve it. Now let's see if the program will automatically solve it. Could be tricky, but maybe it'll do it. So I put that up there and I say, program, solve for the mantissa. And there it is. Notice the 1 here, it's still true. So to get the mantissa, you use this formula. And notice that 83888,608, that is 2 to the 23rd. That would be another way of writing that. So the mantissa is this thing here. And let me less decimals. We don't need all those decimals because they're always going to be integers. And let's check it. There's the mantissa as calculated by the program, and there's calculated by the formula. So that's how we can go directly from x to the x and the mantissa. Now, anything else we want to say here? Well, let's just play for a minute. So I think we've covered all the points, but just so we understand some of the details here, suppose I wanted to end up with an exp of, let's say, 4 down here. An exp of 4. What would I plug in up here? Well, I would say let's try 2 to the 4th. And I don't get 4 here. I get 131. But I get 4 here, and that's really what I meant. I suppose I wanted to get a 4 down here. I plug in 2 to the 4th. And so any power of 2 is going to show up as a number down here and all zeros over here. Because when you have all zeros over here, this part here is just 1. Now, suppose I wanted to get a number, let's go over here. Suppose I wanted to see a mantissa with a 1 in, say, this slot here. And I'm not concerned about this at all, so I can leave that the same. I would say times 1 plus. Now, this is the 23rd slot, really the 22nd, because it starts at 0 and you go 23, so it goes 0, 1, 2, 3, 4, blah, 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 blah. This is the 22nd position. So you want to say the bit map, or the bit in the 22nd position is 1, so that means this has to be 1 times 2 raised to the 22nd over 2 raised to the 23rd. And that didn't do it. So we got to think about that for a second. Okay, yeah, here's my problem. I don't want to divide. Now this division by 2 to the 23rd is just the mantissa, not the 1. So I don't want to divide the 1 by this. I just want to divide the mantissa part, which is this part here. There it is. So that's how I would put a 1 there. And again, it doesn't matter what's going on over here because the mantissa is not determined by, you put any multiple of 2 out here you want. That's just going to influence this piece over here. Suppose I wanted to have a 1 here and a 1 in the next slot. Well, I'd go to this piece here. Let me actually put it in big form. Might be easier to see what I'm doing there. I'm going to take this, and I don't need that 1 there. Let me put it in parentheses. And now I'm going to add to that, undo. I'm going to add to that 2 raised to the 21 power. And let's save that. And there it is. I pop a 1 into that next slot. Suppose I want to put a 1 down here now. I got to go in here and put a 2 to the 0. Let's actually do it that way. We know that's going to be 1, but let's keep the form and save that. And there it is. And finally, suppose I want to put a 1 there. Well, let's put it in order here. I'm going to do a plus 2 raised to the 1 and do a save. And there it is. So, all I'm really saying here is, how do you think of this collection of bits when you want to think of it as a decimal number? Well, you think of it as a sum of things like this, where if there's a 1 here, then you include that power in the decimal in the decimal version of the number. And I think that's enough for this.